Hi everyone. Now we are at lecture number 12, sequences and series. So continuation to last lecture, that is comparison test, problem number 17. Yeah, look at this problem. So find the convergence status of the series 1 upon n cube n plus 2 upon n plus 3 whole raised n. Okay. Now look at this. Directly I am proceeding by limit comparison test, or you can verify from the beginning whether we can apply geometric series or not, we can apply telescoping series or not, or nth term divergence test or not. Like that you can verify. Compulsory how to verify, then only can get some ideas. Directly don't apply limit comparison test, because now we are discussing this problem here. That means after limit comparison test we are discussing, therefore directly limit comparison test you can apply. Okay, if it comes in exam, what to do? That's why you have to practice all the tests one by one. You have to verify. If the first test is fails, for example geometric series is fails, then go to the next test, like that. Okay, you should have a complete grip on that all the tests. Okay, yeah. So now here an is nth term of the series is 1 upon n cube, 1 upon n cube, n plus 2 upon n plus 3, n plus 2 upon n plus 3 whole raised n, whole raised n. Okay, and most of the students are asking, sir, how to choose bn. Still students are having some doubts about this. One trick is, as n becomes very large, this is approximately equals to what? In that sense we discussed it. So n plus 2 is approximately equals to n. So n to the power of n, because power n is there, numerator, and denominator n cube is already there, into n plus 3 is approximately equals to n, as n becomes very large only. Okay, n plus 3 can be written as n only, but power n is there, power n. So n power n will be cancelled out. So you will get 1 upon n cube. So this will be your bn. Okay, so therefore you have to choose bn as 1 upon n cube. This is one way, or you can choose like this also, or let bn is equals to, see, numerator maximum nth power of which term you can take common. This is the second way of choosing bn. Okay, you look at both numerator and denominator. From the numerator, maximum nth n power of which term I can take common. So here n power n I can take common maximum, therefore numerator will be n power n. Okay, and denominator n power n into n cube, so that is a maximum n cube into n power n. This is a maximum n power we can take common. So overall now n power n will cancel out. So finally we will get 1 upon n cube. Listen once again. Maximum n power you take common from the numerator and denominator. That's it. So from the numerator, maximum n power is n. Maximum n power will be n power n from the numerator. That's what n power n. Denominator n power 3 into n power n I can take common maximum. That will be the maximum term. You don't say only n power n from the denominator, because n power n is one term and n power n into n cube is there. In this, which one is maximum? This one is a maximum. That's what I'm telling. Maximum which n power you can take common. So maximum n power 3 into n power n I can take common from the denominator. That's what you take it and cancel out the similar terms. They will get 1 upon n cube. So this is bn. Then go to the limit value of the ratio of an and bn. So limit n becomes large, an upon bn, an upon bn. This will be, so limit n tends to infinity, limit n tends to infinity. Now what is an now? An will be 1 upon n cube, 1 upon n cube, n plus 2 upon n plus 3, is it, whole to the power of n. This is what? An upon bn. Bn will be 1 upon n cube, so n cube by 1, n cube by 1. So in this, n cube and n cube similar terms cancelled out. So what will remains? This is equivalent to limit n becomes large, n becomes large. Okay, n plus 2 upon n plus 3 whole power n. Okay, and this will be limit n tends to infinity. From the numerator n power n I can take common, so numerator n, sorry, so 1 plus 2 by n, right, inside the bracket 1 plus 2 by n whole to the power of n. So power n I am applying separately for numerator and denominator. Similarly, denominator also n power n I can take common. So 1 plus 3 by n whole to the power of n. So inside you take n common. So since power n is there, n power n will comes out like that. Okay. So therefore n power n will be cancelled out. Now what will remains now? So this will be limit n becomes large. Limit n becomes large. 1 plus 2 by n whole to the power of n. This is numerator divided by limit n tends to infinity. Okay, 1 plus 3 by n whole to the power of n. This is quotient rule. By quotient rule I am doing it. Okay, so since we know the formula, what is that? So since we know the formula, limit n tends to infinity, okay, 1 plus x by n whole to the power of n, and this will be e power x. Already we have seen this, look at once. So by using this formula, so what will be the required limit? So since by using this formula, instead of x you are having your numerator, in the numerator 2 you are having, in the denominator 3 you are having. Therefore this limit value will be e square by e power 3. Okay, so which is 1 upon, so therefore limit n tends to infinity, limit n tends to infinity, an upon bn value, what we got? 1 upon e. 1 upon e means 1 upon 2.73, right? 2.73. That means which is less than 1. So this is L value, right? So this is L value and this is L value which is less than 1. Limit value is 1.2, 1 by 2.73 less than 1. So it's a finite number less than 1. Therefore, what is the conclusion? Therefore, by comparison test, limit comparison test, not comparison, limit comparison. So by limit comparison, so series, what I want, an and bn both converge or diverge together, but here what I have chosen series bn. So series bn is nothing but series 1 upon n cube is converges by using converges by p series test, right? Because p is equal to 3 by p series test. P series test. So therefore finally what I can say, so therefore series 1 upon n cube, 1 upon n cube, n plus 2 upon n plus 3 whole to the power of n is converges. Okay, so this is the final conclusion by using limit comparison test. Similarly, problem number 18, look at this. So here denominator is not given, only linear function is given. So non-linear function, but it is not a fractional function, right? So then to apply limit comparison test, already this problem I did. So directly by nth term divergence test you can do it by first method, complete it, first method. Directly we expand it. So series n plus 1, sorry, root n plus 1 minus root n. So nothing is given means limits you have to take 1 to infinity. Okay, so we expand it now. So first term n is 1, so root 2 minus root 1. Okay, plus next term n is 2, root 3 minus root 2. Okay, plus n is 4, root 4 minus root 3. N is 3 I am taking, plus up to so on. What will you get? Root n plus 1 minus root n. Okay, plus up to so on. So these kind of terms. So now you look at the nth partial sum Sn. So what will get Sn? Sn will be this entire thing, right? So root 2 minus root 1. Okay. Next one plus root 3 minus root 2. Root 2. Plus root 4 minus root 3. Root 3. Plus up to so on. Sn means sum of first n terms. This is nth partial sum. Sequence of nth partial sum, nth term, Sn. Okay. So root n plus 1 minus root n. Okay. Now look at first bracket first term, second bracket second term will be cancelled out every time. Okay. So look at, and from these two, first I am taking now this one is the first bracket first term, second bracket second term will be cancelled out. Minus root 3 plus root 3. Likewise, if this is first bracket, next will be second bracket. Root 4 minus root 4 will be cancelled out. Similarly, in front, there is one more bracket here. Let us call this as first bracket, this is second bracket. First bracket, first term, second bracket, second term will be cancelled out likewise. So what will remain here indirectly? So minus root 1, okay, and plus root n plus 1 will remains. Okay, so now limit n tends to infinity. What will be Sn? So limit n tends to infinity minus root 1 plus root n plus 1. This will be, what will get? Infinity you will get. So therefore, what I can say conclusion. So therefore, sequence of nth partial sum Sn is diverges. So once sequence of nth partial sum is diverges, therefore corresponding series also diverges. Minus root n. So this is by basic definition I am concluding is diverges. So this is without using limit comparison test. Or you can do it by limit comparison test also. Here conclusion, what I got here, conclusion is diverges, right? Let me do it by second method by using limit comparison test. Okay. So second method. So first an is what? Root n plus 1 minus root n. This is an. Okay. Now rationalize this. So root n plus 1, because to apply limit comparison test, I want fraction, right? So into root n plus 1 plus root n divided by root n plus 1 plus root n. Okay, so this will be numerator a minus b into a plus b, a square minus b square, right? So n plus 1 minus n numerator, and denominator root n plus 1 plus root n. Okay, now what will remain here? Simply n cancelled out, right? Here, so minus n plus n cancel out, only 1 will remains. So therefore 1 upon root n plus 1 plus root n. Understood? Now how to choose bn? So let bn is numerator maximum n power nothing, right? So 1 only, because there is no n term in the numerator. Denominator maximum root n I can take common from both the terms, right? So I can take root n common from both the terms. So here I can take root n common. Here also I can take root n common. Overall maximum term is root n only. So let us choose bn is 1 by root n. So let us compute now the ratio, limit of the ratio. So limit n tends to an upon bn. So limit n becomes large. What is an? An will be 1 upon root n plus 1, okay, plus root n into root n by 1. Okay, so now root n, so limit n tends to infinity, root n divided by denominator I am taking one root n common. So inside what will get? Root of 1 plus 1 by n, right? So inside n I am taking common, inside the root 1 n I am taking common, so that outside root n will comes out. So plus 1, because I am taking root n common. So therefore this root n out. So after applying limit, what will get? Limit n tends to 1 by root 1 plus 1, indirectly 1 by 2 I am getting, 1 by 2. So 1 by 2, this is L value which is less than 1. So you are getting a finite value. So therefore by limit comparison test, both series an and series bn converge or diverge togetherly, isn't it? So therefore series bn here, what is series bn? Series bn will be 1 by root n, 1 by root n is diverges. Why? By using p series test. Diverges by using p series test, because what is p here? 1 by 2, right? N power 1 by 2, p is 1 by 2, 1 by 2 less than 1, so that's what it is, diverges by p series, by using p series test. So therefore by limit comparison test, final conclusion is root n plus 1 minus root n diverges. That's it. So here also I got the conclusion diverges. And you may get doubt here. Instead of choosing 1 by root n, if I choose 1 by n square, what happens? This kind of doubts generally you may get. So if you choose 1 by n square, what happens? Let me do here. If you choose 1 by n square, what will be the limit value? So that means an by bn I am computing, an by bn. So here directly I am computing what is an by bn. So instead of root n I will get n square, right? So n square by denominator root n plus 1 by plus root n. Root n plus 1 divided by root n plus 1 plus root n. So if you take root n common, what will you get? So root n half time will be cancelled out, numerator n to the power of 3 by 2 you will get. Okay, and denominator 1 plus 1 by n plus 1 you will get, because root n I have taken out. Okay, now if you apply limit n tends to infinity, what you will get? So therefore limit n tends to infinity, let me do here. So limit n tends to infinity, an by bn I am doing. Okay, apply n tends to, so infinity by 2 you will get, that means infinity you are getting. So by limit comparison test, third statement, by third statement you are getting L value is infinity and bn should diverge, then only an converges. Look at third statement of limit comparison test. What is the requirement? If limit value is infinity and bn diverges, then the conclusion is a1 diverges. Okay, and here, so and what is series bn here? Series bn is 1 upon n square, but this is converges, therefore you cannot apply the test. Understood? Look at the limit comparison test, third statement. If limit value is infinity and bn diverges, then conclusion is an diverges. Here limit value is infinity and bn converges you are getting, so therefore you cannot apply test. Here you should get bn diverges, then only I can conclude an diverges. So this is because of by choosing an is n square, 1 upon n square you have chosen. Okay, you have chosen bn is equal to 1 upon n square you have chosen. That's why here the result is not getting applied. So you cannot apply the theorem, limit comparison test theorem you cannot apply here if you choose bn is equal to 1 upon n square. Hope you understood this clearly. If not, you listen once again. Okay, similarly, next problem number 19. Find the convergence status of the series n is running from 1 to infinity, n into e power n upon n square plus 1. So this one again same, an is what? N into e power n upon n square plus 1. So now let bn is choose bn. So numerator maximum n into e power n will be common, denominator n square is common, so finally we get e power n by n. So this is your bn. Okay, this is your bn. Then find the limit of the ratio, limit n tends to infinity. Okay, an by bn, what will you get? So limit n tends to infinity, what is an now? N into e power n upon n square plus 1 into what is bn? So n upon e power n divided by, right? So that will be cancelled out, that will be reciprocal. So e power n cancelled out. So finally what will get? So limit n becomes large, numerator n square divided by n square plus 1. So what will get limit value? N square is out, right? So limit n tends to infinity. Limit n tends to infinity. What will you get? So n square divided by n square is common from the denominator. So 1 plus 1 upon n square. Okay. So therefore this n square is out. So final limit value is just 1 by 1, which is 1. So 1, this is L value and this is less than 1. So therefore by limit comparison test, first statement. So by limit comparison test, so series Bn status I want. So both converge or diverge together, right? So what is limit? So series Bn e power n by n. So our goal is to find the convergence status of this series now. Okay. Now let us find the convergence status of this. So here Bn value I got. Okay. Yeah. So now limit n tends to infinity. I want to use here nth term divergence test. So limit n tends to infinity. What do you have? En upon n. If you apply limit directly, e power infinity is infinity by infinity. Infinity by infinity you are getting. Therefore, go to the L'Hospital rule. So limit n tends to infinity. E power n derivative is e power n only. Okay. And denominator derivative is 1. So finally you are getting, if you apply limit value e power infinity by 1, which is infinity only. So which is not equal to 0. So therefore by nth term divergence test, by nth term divergence test, what I can say, series Bn is diverges, which is series e power n by n is diverges. So now we got this series is diverges, therefore the given series is diverges. So therefore by limit comparison test, diverges. That's it. Look at how we have done. So here our main goal is, what is the convergence status of this series? You can use whatever the test, like if it is applicable. We start with again from integral test or geometric series, telescoping series, comparison test, limit comparison test, whatever. You can use all those tests. What we want, what is the convergence status of this series Bn? Okay, if this series Bn is converges, then An converges. If series Bn is diverges, then An is diverges. Series An is diverges by limit comparison test. That's what. Okay, so therefore this series is diverges. Okay, so for the same problem, if you choose Bn is okay, take it exercise. Let you choose Bn is equals to 1 upon n square once. You try and proceed. At the end, you will conclude that we cannot apply the test. That kind of conclusion you may arrive, right? The limit comparison once you try. Okay, if you take Bn is 1 upon n square, we cannot apply limit comparison test. Such kind of statement you will get at the end. So therefore we have to choose compulsory Bn should be this one only, e power n by n. Okay, next one last problem by using limit comparison test. Look at this. It's an interesting one. Find the convergence status of the series tan 1 upon n. So therefore An is tan 1 upon n. Okay, so let us proceed one by one. So first one, I want to apply geometric series. So tan 145, or tan 1, right? Tan 1, tan 2, tan 3, tan 4, or tan 1 by 2, tan 1 by 3. So it is not a geometric series, therefore geometric series cannot be applied. Next, it is not a telescoping. Is it telescoping? It is not a telescoping. And next, nth term divergence test, limit n tends to 1 by infinity 0, tan 0, 0. You are getting 0, therefore you cannot apply nth term divergence test also. Likewise, you verify all those things. So then I'm going to apply here limit comparison test. So by using limit comparison test, so I need to choose a proper bn. Okay, how to choose bn is here a little bit tricky one. I am choosing bn like this. Let bn is 1 upon n. Why I'm choosing 1 upon n, you will get into know the logicness. So then go to the limit of the ratio value. Limit n tends to be an by bn. Okay, what is this? So limit n tends to infinity. What is an? Tan 1 upon n. Okay, tan 1 upon n. What is bn? 1 upon n. Okay, so now here what I am doing is, let see if n tends to infinity, listen carefully. If n is reaching to infinity, therefore 1 upon n is reaching to which number? Can you guess? N is reaching to infinity, therefore reciprocal both 1 upon n goes to 1 upon infinity, right? Is nothing but 0. So therefore 1 upon n goes to 0. Now I am setting, so let 1 upon n is equal to some theta. Let us take theta. I am renaming. 1 upon n name is theta. Now let us come to this uh, limit value. So limit n tends to infinity. Limit n tends to infinity. So instead of writing limit n tends to infinity, n is tends to infinity is nothing but 1 by n tends to 0. Yes or no? So this is 1 by n tends to 0. Both are same. N is reaching to infinity is similar to 1 by n tends to 0. 1 by n tends to 0 here. And tan 1 upon n, tan 1 upon n divided by 1 upon n. Okay. And this will be, so limit theta tends to 0. 1 by n is theta. Tan theta by theta. What is this value? You have seen already in PUC. Limit theta tends to 0, sin theta by theta, cos theta by theta, tan theta by theta. If you apply direct limits, what will you get? 0 by 0 form you will get. Look at tan 0, 0 and 0. So if you get 0 by 0, what to do? Go to L'Hospital rule. Now if you go to L'Hospital rule, what you will get here? So limit theta tends to 0, tan theta derivative, secant square theta, right? Numerator derivative. And denominator theta derivative is 1 with respect to theta you are doing. Now apply limit theta tends to 0, secant square theta is 1. So therefore by limit comparison test, first statement, both converge or diverge together. So therefore, and series Bn, what is series Bn? Which is series 1 upon n is diverges. Is harmonic series, right? By using P series test, it is diverges. Diverges by P series test. Because P is equal to 1 here by P series test. So therefore, by limit comparison test, both converge or diverge together, right? By limit comparison test, series an, which is series tan 1 upon n, is diverges. That's it. So you make sure that before applying limit comparison test, the term should be positive. That you should take care. I am not verifying here. If the terms are more than 0, then only we can apply limit comparison test. You look at the theorem statement. What are the requirements? First, an should more than 0, I have written, right? So clearly here also it is more than 0 only. For all values of n, tan 1 by n is always more than 0. Similarly, previous problem also all the terms are more than 0. Then only we can apply. Otherwise, we cannot apply. Remember. Sometimes minus tan 1 by n, so you cannot apply for minus tan 1 by n. You can bring minus to outside, then now you can apply tan 1 by n. Later I can multiply with minus. That's different issue. But before that, term should be positive. That is compulsory for limit comparison test. Okay. Yeah. Next one, theory number 9, D'Alembert's ratio test, or simply ratio test. Here what are the requirement? Let an be a series with positive terms. Positive terms means here ans are more than 0. Positive. Non-negative means more than or equal to 0. Here positive terms means an is more than 0, compulsory. then only we can apply this ratio test or D-Alembert ratio test. And suppose that limit n tends to infinity an plus 1 by an value is L. So that means we need to compute the ratio again. An plus 1 by an value we need to compute. And assume that limit value is L. Then first conclusion, the series converges if that L value is less than 1. Okay, L value is less than 1. Can I take that L value is minus infinity? So that minus infinity is less than 1. Now can I say that, so limit value is minus infinity, for example, let's say. So minus infinity is less than 1, true. So can I say that series converges? Limit is reaching to minus infinity means what? It is diverges. But here what I'm getting is series converges. Look at here, that's why I'm taking terms are more than 0. The terms are more than 0. How the limit value is negative? It will not be happens, right? Because terms are positive. It is positive only. Limit value how can be negative? It cannot be negative. So therefore this ratio will be always more than 0. Limit value is always more than 0. Limit value. Understood? It is positive L only. Positive L which is less than 1 indirectly. Then the series converges. And the second statement, second conclusion, the series diverges if that limit value is more than 1. And the test is inconclusive if L is equal to 1. For example, if the ratio of the limit is 1, then this test cannot be applied. Then you can go to another test. That means by using this ratio test, we cannot conclude the convergence status of the series if L is equal to 1. Inconclusive means that one. We cannot conclude. That is called inconclusive. Cannot conclude means doesn't mean that series diverges. We cannot say. We can apply another test. It means. Okay. The proof is not required. If you are interested, I will provide in the PDF file the proof of this ratio test. It is not required. Okay. Yeah. Let us do one problem depending on ratio test. Find the convergence status of the series n is running from 1 to infinity 1 upon n factorial. Already this problem I did by comparison test I did. So 1 upon n factorial is less than or equal to 1 plus 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 4 3. I generated geometric series which is converges, therefore lower bound converges. Have you remembered? That is by using comparison test I did. Now same problem by using ratio test. Look at single problem we are doing in a different methods. The only thing is you should have a grip on the test. Once you're having a complete grip on the test, you can play with the problems. Otherwise, problems will play with you. So do more number of problems to get a complete grip on the convergence of the series. Okay? Yeah, let me do this. Now what we want? First, you retrieve what is an. An is 1 upon n factorial. So to apply ratio test, what we required? We required an plus 1 also, right? Then what is an plus 1? An plus 1 is 1 upon n plus 1 factorial. Wherever n, there you write n plus 1. That's nothing else. N plus 1 factorial. Okay. Now, next what do you want? Limit n tends to infinity, the ratio value I want, right? An plus 1 by an by theorem. And this value I want. So limit n tends to infinity. Limit n tends to infinity. An plus 1. That means 1 by n plus 1 factorial. Okay. Now what is an? 1 by n factorial. That means n factorial by 1. Okay. So therefore limit n tends to infinity. Okay. N factorial by n plus 1 factorial. Now simplify the denominator. What do you get if you simplify the denominator? So limit n tends to infinity. Limit n tends to infinity. N factorial as it is. Okay. Look at the denominator n plus 1 factorial. See, look at 5 factorial I can write as 5 into 4 into 3 into 2 into 1, right? Okay, and this can be written as 5 into 4 factorial. Can I write? Check once. So from here onwards, 4 into 3 into 2 into 1 can be written as 4 factorial. So when 5 is writing out, so 5 factorial can be written as 5 into 4 factorial. Or you can write this one as 5 into 4 into 3 into 2 into 1 is nothing but 3 factorial, like this. Same idea I want to apply here. So therefore n plus 1 factorial can be written as n plus 1 into what is the before number of n plus 1? N. So n factorial I can write. Same like this. 5 factorial is 5 into what is the number before 5? 4. So 4 factorial. Same. N plus 1 factorial. N plus 1 into n factorial. So now here n factorial is out. And now you apply the limit value. So limit n tends to 1 by n plus 1 is, so 1 by infinity, which is 0. Now what is L value? L value is 0, which is less than 1. Look at less than 1. First statement. If L is less than 1, the series converges. So therefore, conclusion. So therefore, by ratio test or D-Alembert ratio test, whatever. By ratio test, the series 1 upon n factorial converges. By comparison test also, I proved it is converges. That's it. How simple it is. So no need to find what is proper upper bound or proper lower bound. Proper means convergence upper bound. Lower bound means divergence lower bound I want to apply comparison test. But here it's not required, just you need to find the ratio an plus 1 by an. But how to remember when we can apply ratio test? The first, you look at the problem, if the terms are positive we can apply, and moreover, if n factorial, if the factorial terms are present in the problem, then ratio test is applicable. That means most suitable method, not applicable, most suitable method. If the factorial terms are present in the problem, okay, that I will do as a note. Next, similarly, problem number 2. Look at this problem. Yes, same here. Look at factorial term is present, so we may apply ratio test. By using another test also we can do it, but suitable method is ratio test. So now here an is n plus 1 factorial upon 3 raised n. Okay. Now what is a n plus 1? A n plus 1 is, instead of n you write n plus 1. What will you get? N plus 2 you will get, right? N plus 2 factorial upon, what will you get? 3 power n plus 1. Instead of n just you write n plus 1. And next what I want? Find the ratio, limit of the ratio. Limit n tends to infinity an plus 1 by an. First an plus 1. Okay. Limit n tends to infinity. What is an plus 1 here? N plus 2 factorial. N plus 2 factorial upon 3 power n plus 1 divided by an. An means n plus 1 factorial by 3 power n. So if you reciprocate it, 3 power n will go as a numerator divided by n plus 1 factorial. Okay. Now again you apply the same technique what we applied just now. 5 factorial can be written as 4 into 5 into 4 factorial, like that, right? So n plus 2 can be written as n plus 2 into, next before number is n plus 1, so n plus 1 factorial. Can I write? Look at the numerator. N plus 2 factorial can be written as n plus 2 into n plus 1 factorial, and denominator 3 power n into 3 I can write. 3 power n into 3, and here don't modify this, you write as it is, 3 power n divided by n plus 1 factorial. So clearly n plus 1 factorial cancelled out. Okay. So n plus 1 factorial is out, n plus 1 factorial is out, 3 power n is out, 3 power n is out. What will remains? So now limit n tends to infinity. What will remains? N plus 2 divided by 3 only, right? Check once. Yeah. So now this will be infinity. Infinity. So what you got? Infinity, which is L value, which is more than 1, right? More than 1. Therefore, by limit comparison test, what I can say? So therefore, conclusion. Therefore, it's not limit comparison test, by ratio test. Sorry, by ratio test. By ratio test, the given series is diverges. The given series diverges. Okay. That's it. Okay. Next one. Similarly, problem number 3. Find the convergence status of the series 1 by 2 plus 1 into 3 by 2 into 5 plus 1 into 3 into 5 by 2 into 5 into 8 plus up to so on. So first you need to find the nth term of the series. So let me, first write the series 1 upon 2 plus 1 into 3 divided by 2 into 5. Look at the numerator, only odd terms you are getting, right? So 1 into 3 into 5 upon 2 into 5 into 8. So plus up to so on. This is equals to series. N is running from 1 to infinity. You observe the numerators 1, 1 into 3, 1 into 3 into 5. So numerator I am writing as 1 into 3 into 5 into, okay, up to so on. I am writing 2n minus 1 because all are odd terms you are getting, right? So substitute n is 1, what do we get? 2 minus 1, 1. So first term is 1, look at here. Substitute n is 2, n is 2 here. 2 into 2, 4, 4 minus 1, 3. Look at next 1 into 3. Up to 3 you have to write, okay? Next substitute n is 3, n is 3 means what here? 2, 3 is a 6, 6 minus 1, 5. That means up to 5 you have to write, up to 5. Up to 5 means 1 into 3 into 5 like that. So denominator, first term is 2, next term is 5, so next term is 8. So can you guess what will be the nth one? So nth one will be, so 2's and alternatively even, so 3n minus 1 will be that. So that means you will get alternatively evens. So 3n minus 1, substitute n is 1, 3 minus 1, 2, up to 2 you have to write expansion. So up to 2 means first term is only 2 only, look at here. Listen carefully. Next, how to get 2 into 5? This is second term, right? Substitute n is 2 here, 3 to the 6, 6 minus 1, 5. 6 minus 1, 5. So next term is how much? 5. So first term is 2, next term is 5. So 2 into 5. Next 2 into 5 is same. Next term we need to find. Substitute n is 3. 3 is a 9. 9 minus 1, 8. So 8. So 2 into 5 into 8. Likewise, can you guess what will be the fourth term here? Substitute n is 4 here. 4 to the 8. 8 minus 1, 7. Up to 7 you need to write. 1, 3, 5 is as it is. So therefore 1, 3, 5, how much? 7. Because the substitute n is 4 here. 4 to the 8. 8 minus 1, 7. Up to 7. Denominator n is 4, 4 3 is a 12, 12 minus 1, 11. So 2, 5, 8 same, but 11 we need to write extra, last one. 2, 5, 8, 11. This is fourth term, like this. Okay, hope you understood. Yeah, so this is nth term. So therefore clearly what is an now? So an is 1 into 3 into 5 into up to so on 2n minus 1 divided by, compulsory nth term is required for apply ratio test because we need an plus 1, right? And we require ratio also. If it is not given, we have to find like this nth term. If nth term is given, no need to worry. Next, what is an plus 1? An plus 1 is wherever n, there you write n plus 1. So 1 into 3 into 5 into, yeah. Instead of n, you write n plus 1. If you write n plus 1, so 2 into, okay, so 2 into n plus 1 minus 1, right? Instead of n, I am writing n plus 1. 2n plus 2 minus 1. So 2n plus 1 will get. So therefore here 2n minus 1 and next one is 2n plus 1, right? 2n plus 1 divided by 2 into 5 into 8 up to so on. Instead of n, you write n plus 1. And then again, so 3 of n plus 1 minus 1. So 3n plus 3 minus 1. So 3n plus 2 you will get. So here 3n plus 2. So first nth one is 3n minus 1. n plus 1 will be 3n plus 2. Check once. 3n plus 2. 3n plus 3. So 3n plus 2. Yeah, fine. So therefore, this is equals to. So finally, so now let us find the ratio of the limit. So limit n tends to an plus 1 by an I want. Okay. Find out this. Limit n tends to infinity. Okay. Now what is an plus 1? 1 into 3 into 5 into up to so on 2n minus 1. Okay. 2n plus 1. You may get out why I am writing again 2n minus 1 because this is nth term, right? N plus 1th term means what? Next term. So 2n minus 1 is the nth term. What is the next term? Next term is 2n plus 1. So this is n plus 1th number. This is nth number, like that. Okay, that's right. So this is n plus 1th number is 3n plus 2. What is nth number? 3n minus 1, like that. So divided by 2 into 5 into 8 into up to so on 3n minus 1 into 3n plus 2, 3n plus 2 into, so divided by an, right? An means this one, so you need to write in reciprocal. So 2 into 5 into 8 up to so on 3n minus 1. Don't get panic, most of the terms will be cancelled out. Okay, up to so on 2n minus 1. Just a substitution is over. Now let us cancel out the similar terms. Look at 2, 5, 8 into 3n minus 1. So 2 into 5 into 8 into 3n minus 1. Up to 3n minus 1 cancel out. And similarly 1 into 3 into 5. Here also 1 into 3 into 5. And 2n minus 1. So 2n up to 2n minus 1 cancel out. So finally what are left? So limit n tends to infinity. Now what will be the numerator? 2n plus 1 only, right? 2n plus 1. And what will be denominator? 3n plus 2 only, that's it. So if you apply limit, so limit n tends to infinity. So if you take n out, 2 plus 1 by n, and denominator, again 1 n you take out, 3 plus 1 by n, 3 plus 2 by n. Okay, now you apply the limit. So therefore here n out, n cancel out. So if you apply the limit, what will you get? So 2 by 3 you will get. 2 by 3, this is L value which is less than 1. So therefore, what is the conclusion? So therefore, by ratio test is converges. That's it. So the sum is finite. It is converges means what? This entire, the given, so this entire sum 1 by 2 plus all this sum is finite. You will get finite sum. This sum is finite. Converges means. Okay. So this is how to apply ratio test for this kind of series. Next, problem number 4. For what positive values of x the following series converges? Okay, so before that we want nth term, so let me write that. So 2x plus 3x square upon 8 plus 4x cube upon 8, oh, sorry, 27, right? 27 plus up to so on. Same again, we need to generate what is nth term. So series n is running from 1 to infinity. You look at the denominator. So here nothing is given means 1. So you observe carefully, 1, 8, 27, this kind of terms is nothing but 1 cube, 2 cube, 3 cube, right? So indirectly denominator n cube, let me write that. So n cube. When n is 1, we will get 1 cube, n is 2, 2 cube is 8, n is 3, 3 cube is 27, fine. And look at the numerators, x is there, so x power n I am writing. So first term, if n is 1, x I am getting, look at n is 2, x square, n is 3, x cube, it is okay. And here this term I want, but what are the numerator terms? 2, 3, 4 I am getting. First term is 2, first term is 2 means what? N plus 1 directly over. First term is 2 means n is 1, 2, n is 2, 3, n is 3, 4 over. Look at, like this we can generate. Okay, now this is the nth term, and before applying ratio test, what we want? Term should be positive. So if I substitute x is equal to some minus 1, what will get? Minus 2 I will get. Terms are becoming negative. That's what the question, for what positive values of x question. So since x is positive, all the terms are positive, therefore we can apply ratio test. Okay, so therefore since x is more than 0, all the terms are positive. All the terms, okay, of the series are positive. See, if it is geometric series, you can write, you can apply geometric test also, but you verify whether it is geometric series or not. look at this term divided by this one. What will get? So 1 by 2. So 3 by 16 into x you will get. Now what about this? It is not 3 by 16 into x. Therefore, it is not a geometric series. Likewise, you keep on verifying. But most of the times you can apply either this ratio test or next coming test. I will tell you. Okay. Yes. So all the terms of the series are positive. Then we can apply ratio test. Therefore, what I can write an. So an will be n plus 1 upon n cube into x power n. So this entire thing is, look at this entire thing is my nth term of the series. Therefore, let us take this entire thing is an. Okay. Then what will be next term? An plus 1. N plus 1th term. Wherever n, there you write n plus 1. So n plus 2 by n plus 1 whole cube. Instead of n, we are writing n plus 1. That's it, nothing else. And x power n plus 1. X power n plus 1. And then you apply the ratio of the limit of the ratio. So limit n tends to infinity. An plus 1 divided by an. So this value I want. So limit n tends to infinity, an plus 1 value. So n plus 2 upon n plus 1 whole cube into x raised n plus 1 divided by this term. So it becomes reciprocal. So n cube upon n plus 1 into x power n. That's it. Okay. Now you can cancel out the similar terms. Any terms are cancelled out, you can cancel out. Okay. So n cube by n plus 1. Yeah. Next, to simplify the terms, so which is equivalent to, so this is equals to limit n tends to infinity, n cube into n plus 2 divided by n plus 1 whole to the power of 4, right? Because n plus 1 whole cube into n plus 1 into x to the power of 2n plus 1. X power n plus 1 into x power n. Total x power n plus 1 plus n. So 2n plus 1. Clear? Now you apply limit n tends to infinity. So before that, let us simplify. Limit n tends to infinity. Let us take one n common from the numerator. So n into n power 3, total n power 4, 1 plus 2 by n. 1 plus 2 by n divided by denominator also inside the bracket. Let us take n common, but since power 4, so n power 4 will comes out 1 plus 1 by n. Okay, listen once again, inside the bracket I am taking one n common. So you look at this, and this one also most of the students are asking, sir, how it is n power 4 is coming out. So n plus 1 power 4, right? Okay, then take out n common from inside the bracket. If you take n is out, what will get? 1 plus 1 by n, right? But power 4 is there. Power 4 is there. Then since power 4, so n to the power of 4 is out. 1 plus 1 by n power 4. Apply that power 4 to both the numbers n and n plus 1. That's why n power 4 is out, 1 plus 1 by n to the power of 4. Now these two will be out. Okay, here x power 2n plus 1 is left. X power 2n plus 1. Sorry, it is become down, right? It coming down, sorry. Yeah, so this one I can write as, so x power n will come down 1 by x power n, right? 1 by x power n, 1 by x power n, so that it will be, because it is divided by, right? Look at an plus 1 by an. Divided by an means what? N cube will come in the numerator, and n plus 1 into x power n will come down. Okay, n plus 1 into x power n will come down. So x power n 1, x power n cancelled, only x will remains. So here what you will get? Only x you will get. So therefore, yeah. So what will you get? Final answer? Yes. So only 1 into x you will get. So therefore, what do you get? Limit value. So this is L value. Look at the question now. For what positive values of x the following series converges? So when it is converges, if L value is less than 1, right? So therefore, if if L is less than 1, then the series then the series uh, then the series converges, right? The series converges. So therefore I want L is less than 1. L is less than 1 means what? X is less than 1. So therefore for 0 less than, so instead of writing 0 less than, since the terms are positive, therefore that is obvious. So therefore for x less than 1, the series converges. That's it. The series converges. The series converges, and moreover, since that x is positive here, right? For what positive values of x? So therefore, for 0 less than x less than 1, the given series is converges. Okay, and we need to verify for x is 1. If x is equal to 1, actually you look it back, go back. If I take x is equal to 1, if I take x is 1, what is L value? L value is 1. If L is 1, the test is inconclusive. Inconclusive means we cannot conclude its convergence or divergence. So we need to adapt any other test for its convergence. So if L is 1, what happens? Okay, so if L is 1, I mean x is 1, so now let us take the case 2. So in this case 1, so let us take case 2. So this is a case 1. Okay, so for case 2, if x is equal to 1, for x is equal to 1, what happens? X is equal to 1. Then what is the given series? So given series is n plus 1 upon n cube into x to the power of n, where n is running from where to where? 1 to infinity, right? Now if I substitute x is 1, what is this? It becomes n plus 1 upon n cube. N plus 1 upon n cube, where n is running from 1 to infinity. If I take x is 1, so here L is equal to x is equal to 1. Okay, but by using this test, which ratio test, we cannot conclude its convergence or divergence if I take x is 1. Okay, by general method I am finding for x is 1 the convergence status of this series. Okay, so then this will be equal to, so therefore what is an now here? An is n plus 1 by n cube. Okay, so now let us choose, let Bn is, I am applying limit comparison test. Okay, so this will be numerator maximum n I can take common, denominator maximum n power 3 I can take common. So overall which is 1 upon n square. Let us choose Bn is 1 upon n square. Okay, then find out what is the limit of the ratio. So limit n tends to infinity, an by bn, so which is, so limit n tends to infinity. What is an here? An is n plus 1 by n cube divided by n square by 1. Okay, so if you take n out from the numerator, so overall n cube is out. So what will 1 plus 1 upon n you will get in the numerator, and denominator also n cube is already there, so that will be cancelled out with the numerator. So this is limit n tends to infinity. Okay, now we cancel out the similar terms, n cube is out. Now what is the limit value? Now this is equals to 1, right? It's 1, but this is L which is less than 1. So therefore by limit comparison test, look at only limit comparison test for case 1. So therefore by limit comparison test, by limit comparison test, series, so series Bn, which is series 1 upon n square, is converges by p series test, right? By p series test, because p is equal to 2 here, by p series test. So therefore series an also converges. What is series an here? Series n plus 1 upon n cube is nothing but x is equal to 1 case is also converges. So therefore what I can say now, for x is equal to 1, the series converges indirectly. Okay, the series converges. So for x is 1, the series converges. So therefore overall comment is, what is overall comment? Therefore for 0 less than x less than or equals to 1 now. So from the case 1 I got 0 less than x less than 1 I got here, right? But by case 2 for x is 1 is also converges. But x is 1, for x is 1, we are not concluding by using ratio test. We are concluding by using limit comparison test. So by limit comparison test, x is 1 also, this given series is converges. So overall for 0 less than x less than or equals to 1, the given series converges. So this is a final comment. The given series converges. That's it. So this is the final conclusion. So 0 less than x less than or equal to 1, the given series, this series is converges. That's what is the positive values of x. Okay. So therefore for 0 less than x less than or equal to 1, the given series is converges. So this is the final answer. And with this I'll stop.